Okay, this video is from Chapter 2, Section 7, and the topic is solving equations in one variable. What you'll learn about, we're going to learn about solving rational equations, we're going to learn about extraneous solutions, and we're going to look at some applications. Why we're going to learn this? Applications involving rational functions as models often require that an equation involving fractions be solved. So here's a definition for you. Extraneous solutions. When we multiply or divide an equation by an expression containing variables, the resulting equation may have solutions that are not solutions of the original equation. These are called extraneous solutions. For this reason, we must check each solution of the resulting equation back in the original equation. So here's an example. We want to solve for x. So how do we solve for x? Well, we can clear fractions. This is one technique that we have. What we do is we determine a least common denominator of all the fractions in the equation, and there's only one, x minus 3. So what we do is we go through and we multiply the entire equation by the LCD x minus 3. And it's a distributive property problem. So when we distribute x minus 3 to all the terms in the equation, we get x times the quantity x minus 3. That's x minus 3 times x. X minus 3 times this part of our equation is just 1. And then x minus 3 times 1 is x minus 3. So as you can see, we've cleared the fractions. And then from there we have a quadratic after we simplify. So it's just a matter of doing some quadratic solving. And you can see when we do that, we get a value of 2. And what we have to do anytime we're solving using these techniques, again, multiplying or dividing using variable expressions, we have to check our solution. So this is the check over here on the right. And we don't get a weird value or anything like that. We don't get anything undefined or anything like that in the original equation, so we know that x equals 2 is the solution of the original equation. Here's another one. Determine the LCD, clear the fractions, and solve. The LCD is x, multiply through by x, solve the resulting quadratic. This time we get two solutions. So as long as those two solutions work in the original equation, and they both do, here's the work for it, then we know that each value is the solution of the original equation. Here's a little more complex problem. We have three fractions in our equation, so we need to determine the least common denominator of all of those. And anytime you're determining the least common denominator, everything needs to be factored. So x squared minus 4x plus 3 can be factored into x minus 3 and x minus 1. Our LCD is going to be made up of all the factors that appear in any of these fractions. So we have an x minus 3 that's in at least one of those fractions, and we have an x minus 1 that's at least in any of these fractions. And if there were any other factors, we would include those in our LCD. Now we use the LCD. So the LCD is those two factors. So we multiply the entire equation by the LCD. So here we see the LCD multiplied by the left side, LCD multiplied by the right side. This is the resulting equation. And again, it's quadratic, so we solve this quadratic equation. When we check our solutions in the original equation, x equals negative 1/2 is the only solution, because the original equation is not defined at x equals 3. All right, if I go back to my original equation, if I put 3 in for x in this first fraction, I get a 0 in the denominator, and thus I have an undefined value. So overall, that will not work because the equation is not defined at x equals 3. Here's an application. We want to find the dimensions of the rectangle with minimum perimeter if its area is 300 square meters. Find this least perimeter. So these are common problems, maximizing and minimizing, with dimensions and areas and perimeters. So think about how you would go about solving this problem for a second here, and then maybe pause the video and see what you can come up with, and then we'll take a look at how we go about doing this problem. So the word statement in the problem is that perimeter equals 2 times the length plus 2 times the width. We know that to be true. We're going to let x equal the width in meters. So 300 divided by x is going to give us the length in meters, and that's because area equals length times width. So the area divided by the width is going to give us the length. So the function to be minimized, we're trying to minimize the perimeter, is p of x, perimeter p, is 2x plus 2 times the quantity 300 divided by x, right? So again, all we're doing here is we're taking, we defined x to be the width, so here's x, and we're taking this out, we're defining length to be 300 over x. So that's where this perimeter function comes from. So just to simplifying it a little bit here, we get 2x plus 600 over x. Now we're going to solve this graphically, okay? Solve this graphically. When we solve this graphically, we can find, using the tools on our calculator, we can use the minimize tool to find the minimum value. Approximately 69.28 occurs when x equals 17.32. So the minimum value of the function occurs when 17.32 equals x, and x is defined to be the width. So the width is 17.32 meters. We can use that to calculate the length, which is also 17.32 meters. So the minimum perimeter is 69.28 meters. So here's some review problems for the lesson. I would pause the video, work these out in your notes. When you're finished, play the video, check your solutions. As always, if you miss any of these questions or you have any questions on the concepts or the examples from the video, please be prepared to ask about those in class.